So good evening, Sheffield. This is 200 at 75. The 200-inch telescope on Palomar Mountain is now 75 years old. Originally, this talk was called 200 at 70, but not surprisingly, that was a few years ago. So I've simply updated the title. This picture was taken in 1951, a few years before I was born. But I remember seeing it in a book, probably in the school library, and I thought to myself, what is that? What's it made of? What's it doing there? And then I read in the caption, this image was taken by the world's largest telescope, the 200-inch Hale telescope. And this, more than any other picture, got me started thinking about what is actually out there and how do we study the universe. And I'm also taking inspiration from this book, Glass Giant of Palomar, written in 1939. This little quote, barometer up and humidity down. One of those crystal clear nights when the stars fairly crackle. It's a wonderful book written about how Hale built the 200-inch telescope. I'm not going to give you the full history of Hale's life. I'm going to be looking at the design and construction of the 200-inch telescope. So George Hale was a billionaire whisperer who built large telescopes, the largest telescopes in the world, 40 and then 60 and then 100 and then 200-inch. I'm going to be telling you about how the 200-inch telescope was built, how they selected a site, how they made the mirror, how they made the telescope. And then I'll finish looking at what the 200-inch is doing now, and then I'll finish the talk with some acknowledgements. So, George Ellery Hale. He had a remarkable life and he was very, very important in studying the sun. He generated instrumentation. He built a spectrohelioscope that allowed the sun to be imaged at different wavelengths. But perhaps he's even better known as the person with the vision and the drive to build the world's largest telescopes. That started with the 40-inch refractor at Yerkes Observatory, the largest refracting telescope in the world. And then in Mount Wilson, he saw the 60-inch reflector built and finished in 1908. And then the perhaps more famous 100-inch Hooker telescope finished in 1918. The story of those three telescopes is interesting in their own rights, but I'm going to start the story for this evening in 1918. When the 100-inch Hooker telescope was operational in 1918, that's when Hale said, what are we going to do about the next one? Up to this point, telescopes had been getting bigger and bigger rather incrementally, from 40 to 60-inch, half as much again, from 60-inch to 100-inch, roughly half as much again. But this time Hale said, let's not go to 150-inch, let's go all the way and think about one that is twice the diameter. How are we going to do that? Well, he tried getting funding. It took a long time for him to get the funding he needed for such a large project. In 1928, he approached the Rockefeller Foundation and persuaded them to pledge $6 million to build not only the telescope and the dome, but the entire observatory infrastructure. $6 million back in the 1920s, that would be certainly a fraction of £1 billion or $1 billion in today's money. So where are you going to site such a telescope? Having obtained enough money to build one, where are you going to put it? These days we might think about Canary Islands or Hawaii or Chile, but at the time Hale thought a little more locally. He said, well, all of the important astronomers in the world are in America and specifically the environs of Los Angeles. That sounds like a rather parochial way of viewing the world, but it's true that Los Angeles did indeed contain a lot of the machine shops and optical shops that were necessary to do the sort of work he envisaged. And he didn't want to have an observatory halfway around the world, a long way from his home base. But if you look at where Mount Wilson is, up in the mountains there, you can see that Los Angeles, growing over time, now produces a lot of pollution right next door to Mount Wilson. Also, San Fernando and San Bernardino have grown up, and Mount Wilson is virtually getting encircled by light pollution. So Hale sent out scouting parties to various mountains that you can see in this particular map, and they found that lots of mountain peaks had excellent seeing conditions. Before making a decision, he consulted with his geology colleagues, especially one Professor Richter, yes, Richter of the Richter scale, and asked Richter, are any of these particular sites better than any others? Richter responded by saying, well, if I were you, I would veto this one and this one because they are sitting on the San Andreas fault. Not a good idea. But he said, this one that you've highlighted, Palomar Mountain, a little bit southeast of Los Angeles, that looks interesting, he said. If you say that's a site with exceptionally good seeing, then I can recommend it as a geologist, because Palomar Mountain is a slab of granite, 30 miles long, 10 miles wide, 25 miles deep. It is a few trillion tons of solid granite. It is a great place to have a nice solid foundation for your telescope. So Palomar Mountain was chosen as the site for the new 200-inch telescope. It's far enough away from Los Angeles not to be a problem, and south of Palomar there is a little place called San Diego, but that's about 60 miles away, and at the time San Diego wasn't too large. It of course has grown over the years, but still Palomar Mountain is a site of relatively good seeing. It's actually a rather beautiful place depending on what time of year you visit. I actually went there back in 1982 in May. Looks like I might actually be wearing the same shirt, I'm not too sure. But when I visited, it was a shirt sleeves day, beautifully warm, and it's difficult to appreciate just what it's like in winter because of its altitude at 1,700 meters or 6,000 feet. It can get very cold in winter, and you need to employ people to shovel snow off the top of the dome. It's sitting there at 1,700 meters. But one of the problems, although it's nicely remote away from population areas, it did have the problem that the only way of getting anything up to the top of the mountain was this rather windy road called the South Grade. Something like 12 miles long, but you can see the number of hairpin turns that you have to go through. And remember, it's not just the telescope that needs to go up that road, it's essentially every piece of equipment that you need to build an observatory. Every piece of steelwork, as well as the telescope and its mirror. So Hale has got $6 million of backing. He's now decided that Palomar Mountain is the place that we're going to put this wonderful new telescope. How is the telescope going to be mounted? Well, astronomers know that there are a number of ways that you can mount a telescope. Let's assume that we're just dealing with equatorial mounts, because in these days Altazer mounts were not a viable option. So you could have a German mount with a counterweight, or you could have a fork mounting, or you could have an English, or sometimes called a yoke mount, which is sort of two forks back to back. You can see that the advantage of the English mounting is that it's supported in two different places, above and below the telescope on the north and south side, so it's extremely rigid and very good for heavy telescopes. It's interesting to note that these three different ways that you could possibly mount a telescope were each incorporated to the three telescopes that Hale built prior to building the 200-inch. The 40-inch Yerkes telescope was on a German mount. The 60-inch reflector at Mount Wilson was on a fork mount. It may not look much like a fork mount because the fork arms are very stubby, but it is indeed a fork mount. And the 100-inch Hooker telescope was in an English or a yoke mount. So the question is, how do you progress from there to the next telescope up? Remember, the next telescope is not simply half as big again. The mirror is going to be twice the diameter. So the whole structure, if you were to simply scale it up, is going to be 8 times the mass. So you have to really worry about the rigidity of the structure. So when it came to thinking about how you're going to scale up the Hooker telescope to something larger, Hale did not want the new 200-inch telescope to suffer from the same limitations that were found for the Hooker, the 100-inch Hooker. Those two limitations, one relates to the mount. You can see from the picture on the left that the telescope can't swing through all possible declination values, because if you move it towards the North Pole, at some point it's going to foul with the yoke mounting itself. In fact, the 100-inch hooker could not reach within 30 degrees of the North Celestial Pole. And it was simply hoped that, well, let's just hope that nothing interesting happens in that part of the sky, and that being able to see the rest of the sky is good enough. But Hale did not want that same limitation to apply to the 200-inch telescope, so he figured that they needed a different way of mounting the telescope. The second limitation that Hale was very acutely aware of was the fact that the mirror was made of plate glass, and that meant that it would expand and contract if the night temperature changed, and it would take quite a while for the mirror to come into thermal equilibrium with the surrounding air. And whilst it was expanding or contracting, the surface of the mirror would distort and not produce nice crisp star images. In fact, it was such a problem that in some cases, if the night temperature was a few degrees different from what they expected, it might be that the telescope was out of commission for hours whilst they waited for the mirror to reach the same temperature as the air around it. So, dealing with one of these problems at a time, what was the solution for the problem with the yoke mount? It was decided that they would still have a yoke mount, but they would have an iconic horseshoe yoke. In other words, still the same idea of the telescope tube sandwiched between two yoke arms, but you can see at the north end the bearing surface is a very large surface of the outside of the horseshoe, and the horseshoe allows the telescope to nestle inside the horseshoe and hence point at the North Pole if that is required. So it can effectively access any part of the sky that's visible from the latitude of Palomar, about 33 degrees north. So that gives incredible stability, but still allows you the access that the 100-inch was missing. So there's one solution to a problem. What about the mirror? This is looking into the side of the 100-inch mirror. So we have the metal coating on the top surface, and we're looking into the side of the mirror itself. And you can see that the glass is a bit of a mess, quite frankly. There seem to be stratification, there seem to be layers of glass, implying that when the glass was poured, perhaps some of it started to set before the next layer of glass was poured in. Not only that, but you can see huge structures within the glass and millions of air bubbles. That means that when the glass is heated up or cooled down, it will expand in a rather irregular way depending on where all these air bubbles are. So again, it's a problem. You can't use this mirror unless it's at a uniform temperature, the same temperature as the air around it. And this again is a problem. So the question is, how do you deal with that? Can you simply take the 100-inch mirror and scale it up to make a 200-inch mirror? And the answer is, well, not really. Because if the mirror is twice the diameter, 4 times the area, if it's twice as thick, that makes it 8 times the mass. It's going to be even slower at trying to come to equilibrium with the air around it. In other words, getting the heat out of the middle of the mirror and getting it to the surface where it can radiate away is even slower. So if it takes a few hours for the hooker to come to equilibrium with its surroundings, it's going to take all night for a 200-inch mirror built the same way to come to equilibrium with the nighttime air. So Hale realized that plate glass would suffer, and the distortions in the surface of a plate glass mirror would just make a 200-inch mirror completely unviable. So he decided to use the latest invention, low expansion glass, what we would now call a type of Pyrex. That's the trade name for a particular low expansion glass. That means even if the temperature does change, the expansion and contraction of the mirror will be much less, and therefore any distortion of the surface will be much less noticeable. But also Hale realised that you've got to get the mass down. You can't simply scale up a 5-ton mirror like the the hooker mirror, you can't scale it up by a factor of 8, because then you would end up with a 40-ton mirror, and that again is unviable. So to avoid having such a heavy mirror, it was realized that you need innovative glass pouring technology. So Hale went to the Corning Glass Works to say, what can we do about this? Let me just remind you how it normally works. If you take a mould and fill it with molten glass, the mould fills up. And so if we think about a pancake, this is of course seen from the side. It would be circular as seen from above. You end up with a pancake of glass if you simply fill an empty mould, and it's approximately flat on its top and bottom surfaces. You would then let it cool down to room temperature. And once it's at room temperature, you would grind the top surface to the right shape and then coat it with a thin layer of metal such as aluminium. But if you decided to do the same with the 200-inch and say, what if we made it the same way as a 100-inch mirror? Because it's so massive, 40 tons of glass, if you wanted to cool it down from the melt, and molten glass would be something like 1500 Celsius, if you wanted to cool it down to room temperature, you would have to cool it very slowly to make sure you didn't introduce any stress in the glass due to the contraction of the glass as it cooled from a very high temperature down to room temperature. It was calculated if you use the same idea as the hooker mirror, then this 200-inch mirror would have to be set to cool over a period of years, possibly as many as 10 years. And nobody was keen on the idea of making a mirror and then spending 10 years waiting for it to cool to room temperature before you could then start grinding the surface. So what did they do about this? They came up with the idea of filling the mould with cores, which are basically fire bricks. And then as the glass is poured into the mould, the glass flows around the fire bricks. That way you use less glass. And it's quicker to cool down. It might take less than a year to cool rather than 10 years. Might still sound like a long time, but spending 10 months or so to cool from 1500 Celsius down to room temperature, that's not so bad. Once it's cold, you can remove the fire bricks, and then you're left with air gaps, and you would then grind the top surface just like you would normally. You would grind it down to the shape you want and then coat it with metal. So you end up with a piece of glass where the front surface looks just the same as before, but the back surface is now full of air pockets and ribs of glass. This makes it very strong, but relatively light. About, less than half of the mass it would be if you simply scaled up the hooker mirror. And that's what they did. This drawing by Russell Porter, I'll show more of these drawings later. This drawing shows a cutaway, as it were, of the mirror sitting in the mirror cell. And you notice that there are various air pockets and ribs of glass that have flowed around the fire bricks, and some of these pockets actually used for these things that look like the heads of car engine cylinders. These are the mirror support pistons that are holding the mirror and supporting the mirror, such that regardless of which way the mirror is pointing, it maintains exactly the same shape. A very important element of the telescope is the mirror support system, otherwise you end up with a large piece of glass which distorts whenever you point it to different parts of the sky. So that's what the mould actually looked like. 200 inches in diameter, about 5 meters in diameter. All of these fire bricks are in place. You see some of them look a little bit triangular, some of them look more circular. The circular ones are going to generate the pockets which ultimately will be occupied by the mirror support system. Also notice a large plug in the middle, because we don't want any glass in the middle of this mirror, because ultimately it's going to be used as a Cassegrain telescope, and we want to send the light through the center of the mirror, which we'll see shortly. So that's how the mold was made, and then it's a question of just generating enough molten glass to pour into this mold. and I appreciate you can't read all the detail here. This is just a schematic of what the Corning glass works looked like in 1934. There's a big tank on the right full of the glass, which is melted by turning this oven up to 1500 Celsius. So basically we have a large tank of molten glass. And then teams of workers with large ladles that look like ice cream scoops, they scoop the molten glass out of the tank and then bring it over here to the casting oven, where they pour the glass into the mould and the glass flows around the fire bricks which have been placed into the mould. Clearly the ladle can only carry a small bit of glass at a time, and so this process is repeated hundreds of times during the day to get all of the required material into the mould. Here's a little video showing it in action. Some workers there are dipping the ladle into the glass, the heave-ho on the other end, and out comes about 100 kilograms of glass in the ladle. The ladle is sprayed with water to stop it melting, and then the ladle is carried over to the oven. So here it is from another angle. The scoop goes into the tank, and then men jump on the other end, and out comes 100 kilograms of molten glass. Excess glass is scraped away. More water is played on the ladle to stop it melting, and then the ladle is taken over to the casting oven, where it is poured into the mould. And that process is repeated hundreds of times. Any glass that is left in the ladle is then poured into a wheelbarrow, which is then taken back to the tank for the material to be recycled. And that process goes round and round and round every few minutes for many, many hours, until something like 20 tons of glass has been poured into the mould. So there's a picture showing you just a little more detail. You can see the weight of the ladle is taken by this rail system, which is designed to get you from the tank to the casting oven. The person at the front makes the decisions as to exactly where the ladle is tipped out to ensure that the molten glass spreads as evenly as possible throughout the mould to make the mirror. And here we see one of the ladles being poured into the oven. I presume the gentleman on the left is a supervisor because he's wearing a hat rather than a flat cap. Now, this was 1934. Unfortunately, that casting didn't work as well as it should have. The fire bricks, which you can hardly see in this image because it's so bright inside the casting oven, but one or two of the fire bricks inside the oven detached during the casting process. And fire bricks are lighter than glass, which means they floated to the surface. Not only that, but some of the bricks of the oven, you can see the entire oven is made of lots of small bricks. Some of the bricks on the inside became loose and fell into the glass. So all in all, the glass was a mess. When it had cooled down a little bit, they tried to recover the bricks that had fallen into the glass or floated in the glass, but basically the mirror was a mess. You can see these huge gouges which didn't anneal out because of either the fire bricks floating or the bricks dropping from the top roof of the oven. If these gouges were in the centre of the mirror, then it might have been possible to grind them out. Remember, the mirror is going to be ground into a parabolic shape, and we're going to lose quite a few centimetres at the centre of the mirror, but unfortunately these gouges were just simply too close to the edge, and it would not have been possible to grind this down to the point where you then obtain pristine glass. You would be down to basically the fire bricks. So they learnt their lesson and had another crack at making the mirror in 1935. They bolted the fire bricks down rather than just trying to cement them down, and that worked fine. So the second attempt worked well. In 1935, they had a working mirror. It took many months to cool down from the melt, but once they had done so and inspected it, here one of the people is looking by shining a light through one of the glass ribs of the back of the mirror, making sure that there was no sign of any stresses in the glass. This mirror shows very nicely the ribbed structure of the back, the fact that we have large voids that are basically just air to reduce the mass of the mirror, and we have these circular pockets, which is where the mirror mounting system is going to support the mirror when it's in its final resting place. Corning were very proud of their piece of glass, and so they produced a number of different pieces of publicity for it. So here, for instance, this gentleman appears to be measuring the size of the Cassegrain hole in the middle. If it's too large, there's not much you can do about it, so I'm sure he's just measuring it just to point out how large it actually is. The mirror appeared in their adverts. The eye that sees 6,000 million miles. Why did they choose that number? Well, it was thought that the 200-inch telescope ought to be able to see something like 1 billion light years, based on experience from previous telescopes. And so they simply converted 1 billion light years into miles and came up with that number. The manufacture of that second mirror wasn't without its own problems. For instance, while it was cooling down from its molten state to room temperature, the nearby river flooded and was in danger of actually hitting the transformers that were feeding electrical power to the ovens, but luckily they managed to avert disaster. They even had a small earthquake over on the eastern side of the USA, but none of that stopped the mirror being declared as this is good enough to use. This is as good as we can possibly make it. So they shipped the mirror from the East Coast over to Palomar, or over to Los Angeles for the optical workshop. There you can see the entire 20-ton mirror on a strap. I'm not sure I would trust that, but there you go. And again, you can see the translucent nature of the mirror. The light is on the other side, and we're seeing the rib structure showing through. Once the mirror arrived at Caltech in Los Angeles, it went to the optical workshop, where a team of 21 men spent the next 11 years grinding it to shape. Or at least it took a total of 11 years. I'll say why that's not quite the same thing in just a moment. So it was quite an endeavour to get this mirror ground, by far the largest one that had ever been attempted. This is the grinding machine. You can see that the mirror rotates, and then a grinding or polishing wheel also rotates and moves backwards and forwards on this gantry, and the gantry moves backwards and forwards. So it looks like at the moment this person is applying some grinding or polishing medium to enable the polishing to continue. For testing purposes, the mirror is moved to the upright position because effectively that's the only way they could do the optical test. So again, you can see the importance of having the mirror supported correctly from the back. It is absolutely critical that the mirror is supported in such a way that whether or not it's facing up or whether it's facing the wall, the figure of the mirror does not change. If gravity did its thing and you didn't support the mirror correctly, then the mirror figure would distort, even if only slightly, when it was moved to different positions. And if you're grinding it while it's horizontal, but testing it when it's vertical, it is absolutely critical that you are testing the same shape that you actually have on the grinding machine. So the mirror support, that's a story in its own right as to how it was designed, but I'm not going to go into details here. It is interesting to note that some of the people working on this mirror, you notice the gentleman on the left has a pipe and the gentleman on the right has a pipe. I can't believe that they were actually allowed to smoke in a room in which they were grinding a mirror to very high precision. Maybe they're just got pipes in their mouth just because that's just their affectation, as it were. The testing was done with the mirror in a vertical position, so the testing was done horizontally, and it was basically a simple knife edge test to make sure that they had the figure correct, spherical at first and then ground into a parabola. You can see the gentleman there doing the knife edge test. So all the time the mirror was being ground and tested, work was going on building the observatory itself. Remember, we're on top of a mountain here made of granite, so the foundations were nice and simple. All you need is to run a few piles into the rock and you have the best foundation possible. So work began in 1936, and there's the walls of the observatory going up. The walls aren't particularly high because it's a very large dome in this particular observatory. So when it got to this particular height, they had to start making the rails on which the dome bogies would actually run. So here somebody is grinding the tracks on which the dome will run. When asked, how smooth do you want these rails? It's purported that Hale responded, well, the nearest thousandth of an inch should do. So it's a very high precision required on something which is so large. So they had to be accurately positioned and extremely smooth. This is because Hale wanted to ensure that when the dome rotated, no vibration was transmitted to the foundation or to the telescope itself. And bear in mind that the dome, when completed, was something like 1,000 tons. So this was a very severe requirement to make sure the dome moved totally smoothly so as not to produce vibration. So once the track was laid, the rest of the dome started to take shape. So this is now 1937. And by late 1937, it started to actually look like an observatory. In order to see what's going on inside, I'm going to use more of Russell Porter's drawings. I'm sure some of the detail in these drawings doesn't come across necessarily on a Zoom call, so I'm going to make available to Darren a link in which you can see high-resolution versions of these drawings just to see how incredible they really are. This particular drawing I'm going to use just as a sort of map to find our way around the inside of the observatory. So let's just blow it up a little bit. Let's just take a crop of the telescope. You can see that there's a cutaway of the mount and a cutaway of the telescope itself. And on the left, there's a little ghost of where the telescope would be pointing if an observer is going to come along this gantry and enter the prime focus cage sitting in the middle of the top of the telescope. And also there's a ghost on the right-hand side showing where the telescope would be pointing if it was pointing at the North Celestial Pole. So let's just dim some of that out a bit and remind us about the optics of the telescope. There's the 5-meter mirror in the bottom. I haven't attempted to show the correct curve of the mirror. So if we were looking at a star that was at the zenith directly overhead, the light would hit the mirror and then come to the prime focus there in this so-called prime focus cage. This is basically the first telescope which is large enough that an astronomer can ride inside and actually take data while sitting inside the telescope. So it might be that they wanted to put a photographic plate here to use the shortest possible focal length to get the widest field of view of the object that they were interested in. In the bottom half of the prime focus cage, down here, below where the observer would otherwise sit, there are a number of mirrors that can fold and intercept the light path before it comes to the prime focus. So there are, for instance, a Cassegrain mirror which could fold down if the observer wanted the Cassegrain focus. So if the Cassegrain mirror came at that position, then what would happen would be the light from the zenith would hit the mirror, hit the secondary mirror, and then come through a hole in the primary mirror. I haven't shown the hole in the primary mirror, but remember that 1 meter hole in the center of the 5-meter mirror. The light would come through there to the Cassegrain focus. The Cassegrain focus is not only a longer focal length than the prime focus, giving you a focal length of close to 100 meters or so, but also it has the advantage that any equipment you want to use to record that light is sitting behind the main mirror, and there's plenty of space for putting large pieces of instrument there. It's been estimated, I'm not sure they ever tried this, but it's been estimated that up to 1 ton of instrumentation could be placed at the Cassegrain focus without significantly affecting the operation of the telescope. The telescope was made to such precision that you could add a ton of instruments and it would still work fine. If that focal length wasn't enough, there is another option whereby the Cassegrain mirror could be replaced with a different mirror, a so-called coude mirror, and a third mirror placed here at the intersection of the right ascension axis and the declination axis. A third mirror would send the light off on a sort of dogleg. So the light would hit the primary, then the secondary, and then hit the third mirror and be sent down the axis, the right ascension or polar axis of the telescope. This would give you a focal length of 150 meters, and it has a real advantage that this point shown in red, where the light comes to a focus, that point does not move. Regardless of the declination to which the telescope is pointing, regardless of the right ascension, the light always comes to focus at this particular point. And that means you can have an instrument in this room called the coude room, which can be as large, as massive as you like. For instance, if you've got a really big spectroscope or spectrometer, that's the place you would put it. This particular focus, because of this sort of dog leg, or if you like, this elbow, this particular focus is called the coude focus because coude is just French for elbow. So a number of different ways that the optics of the Hale telescope can be employed. Let's have a look at how the telescope itself, not the mirror, but the telescope was put together. All the steel work was carried out in Westinghouse over in Pittsburgh, again towards the east coast rather than the west coast. This gives you an idea of the number of people who worked on the steel work. They're standing roughly where the mirror will ultimately be, and they're surrounded by the base ring, which is going to be the ring that supports the mirror cell itself. Here's a few snapshots of various pieces that were made. In the top left, part of the big horseshoe, one of the so-called horseshoe horns, the tube in the top right and bottom left, and what I think is the declination bearing in the bottom right. It was commented that when building something like this, the requirements were such that you are effectively building a battleship, but with the precision of a Swiss watch. Because of course, ultimately, they wanted to be able to point this telescope with arc-second accuracy to a particular chunk of sky, even though the telescope and its mount weighed 500 tons. There's part of the tube assembly coming towards the end of its manufacture. I'm not sure if this is a topping out ceremony, but it must have been fairly important because they've got dignitaries such as, for instance, Professor Einstein sitting here, very interested in the production of this telescope. Einstein, of course, was a theorist, a theoretical physicist, not an astronomer, but he was very interested in the production of the Hale telescope because he figured that the Hale would ultimately be able to either verify or perhaps not verify his theories of gravitation. This gives you an idea of how one of the horns of the horseshoe itself were made. Notice just how thick the pieces of steel are. There's various pieces of strengthening steel on the inside, but if you look at the outside metal and the bearing surface itself, look how thick this is, 4.5 inches thick. And these plates were bent to shape in a 12,000 ton forge press. Yes, that's not a misprint. 12,000 tons were used to press those pieces of metal into the right shape, and then the smaller pieces inside to give it structural strength. There's another piece of the horseshoe, again probably just for publicity. There's not much point measuring it now. It's a bit late to change it if you've actually made it wrong. But again, you can see the thickness of these outer pieces of steel. The horseshoe was made in 3 pieces just because it was impractical to make it as a single piece. So they were made in 3 pieces and then bolted together. Once they were bolted together, they were then put on what I presume was the world's largest milling machine in order to make this bearing surface as smooth as possible. These lugs, of course, would be removed for actual use. That was just for moving the pieces around. But ultimately, when the 3 were put together, they then tried to make the smoothest bearing surface they could get on the outside, because that would dictate how smoothly the telescope turns in right ascension. Once it was Made to the right specification, the 3 pieces would be unbolted and then shipped over from the east coast to the west coast. Other parts of the steel work, this is the south yoke, the horseshoe is the north bearing, this is the south bearing. If you turn it upside down, it looks more like a telephone handset. So here the south bearing is the central circle here, and the big circle in the background and in the foreground, those are what take the circular or cylindrical arms of the yoke, which we can see here. The yoke in the background and the 2 arms coming out of the yoke. Ultimately, the horseshoe would effectively attach to the right-hand side, where you can see 2 gentlemen currently standing in the hollow tubes. It only struck me when I started putting this talk together a few years back that of course the tubes are hollow, and of course people have access to them inside, because one of these tubes has the declination motor. That's where you need to have the declination drive in order to turn the tube, whose axis goes through where I'm indicating there, the middle of each arm. So ultimately, once all the steel work was transferred from Pittsburgh over to Los Angeles, they had to get it up Palomar Mountain, up that windy road. Remember that 12 miles of lots of hairpins, and it's quite a challenge to take that much steel work up a grade like that. Each piece required a number of different trucks. I think in this case we have 2 trucks pulling and I think 1 truck pushing on the other side of this piece, which appears to be part of the horseshoe. Notice the name of the firm that were charged with doing this, Hazard and Sons. As far as I know, everything got up the grade okay. They didn't lose anything down the slopes. I'm sure they had a few problems, but ultimately they got everything up to the top. Everything came into the observatory through a hatch in the observatory floor. Not only do we see the south yoke coming up, this is now 1938, it's also quite a nice view of how the dome in the top part of the picture runs on these various bogies and wheels running on the track that we saw being ground a little earlier. So there's more of it coming through. This is now some of the horseshoe coming up through the aperture in the observatory floor. You can see the south yoke in the bottom left and some of the tube assembly on the left. Once everything is in the observatory, then it's just a question, hopefully, of bolting it all back together again. If it was made in the factory and everything fitted well, then hopefully after transport and arrival at the observatory, everything should just fit back together again. This is quite a nice picture because it reminds us of the scale. There's a worker standing there, and it reminds you what a huge monster this telescope actually is. Again, same thing, the tube is now being put together. Another worker, obviously no need for safety harnesses or hard hats. In those days, there presumably was no such thing as health and safety. So now this is 1939 and the telescope appears to be coming together quite nicely. Here's somebody, at least they are wearing a hat. Okay, it's not a hard hat, it looks more like a fedora, but here one of the workers is looking at the prime focus cage. He's currently where the mirrors would be folded, and up above is where the astronomer would sit if they wanted to use prime focus. I'm assuming the gentleman in the bottom left is an engineer because his sleeves are rolled up, and I think what they're doing here is just checking that the telescope will point as far as it's supposed to in the southern direction. Remember, in the other direction, north, it will point to the North Pole. Here they're pointing it at the south horizon. It's unlikely they ever did any observing this low because remember, on the south horizon there is San Diego. But just to make sure that it can drive to the correct position, they're just taking it to within a few degrees of horizontal. Of course, to move the telescope, they need a motor and some gears. The telescope and the mount weigh something like 500 tons, but they want to be able to point this beastie to accuracy of order arc-second. Hale had specified exactly what he needed the hardware to be able to do. And that meant that things like the right ascension gear wheel needed to be made to very high precision. The right ascension and the declination gears were made to the same sort of precision, and they took almost as long to make these gears as they did to actually grind the mirror, because they needed such fantastic precision. The gear wheel shown here is approximately 10 tons in mass, and it took many years to grind the teeth to the precision required such that they could point the telescope to the accuracy they wanted. So they were using grinding techniques and polishing techniques. I am not sure, but I think this is part of the grinding process. The teeth shape are going to change between this video and the next one. So the teeth are being ground to the right shape and then polished to give them precisely the right shape to engage with ultimately a worm wheel. How do you know when you've got everything right, and how do you know it's smooth enough? Well, you do a test. You get a man with a pipe to run his finger over each of the gear teeth to make sure that they are as smooth as they can possibly be. And then ultimately you test it by running a worm wheel and the worm gear itself to make sure that the drive is essentially frictionless, not frictionless, but zero backlash and as low friction as it can possibly be. So what size motor do you need to drive a 500-ton telescope? Well, clearly it needs to be huge, as you can see from this, where it's getting its daily maintenance of oil. The motor required for tracking purposes is something like 1/12 of a horsepower. Now, okay, tracking doesn't need an awful lot of acceleration because, of course, you're moving the telescope at essentially constant speed. But if you wanted to slew the telescope from one part of the sky to another, even then you would only need a 2 horsepower motor in order to move the entire 500 tons across a large chunk of the sky. Let's have a look at some of these drawings made by Russell Porter. I'm going to skip through them fairly quickly because I think the reproduction that you get via Zoom might not be all it could be, and I'm going to make the full resolution drawings available to you by sending an email to Darren after the talk. But you can see some of the complexity of the drawings made by Russell Porter. Here he shows a cutaway of the right ascension drive. There's a 2 horsepower motor for doing the slewing. There's a 1/12 horsepower motor for doing the tracking. There's even an analog computer shown here, which was designed such that if necessary, you could compensate for variations in the tracking speed. For instance, refraction through the Earth's atmosphere, which is different at different altitudes, not different declinations or different hour angles, but different altitudes. You could compensate for atmospheric refraction. And that was an analog computer based purely on gears and cams, no electronics back in the 1930s and 40s. And it's stunning to see the amount of detail in these drawings. A close-up of how the horseshoe, we're looking up at the horseshoe here, how the horseshoe was suspended on a film of oil to give us essentially zero friction. If they'd simply used ball races or ball bearings, the friction would have been 1,000 times higher. This is detail of the declination drive, which is inside one of the hollow tubes of the yoke mount itself. Looking into the prime focus cage, we'll see more of an astronomer at the prime focus very shortly. But again, it reminds us that there is a gantry which allows the astronomer to get close, and then the telescope is brought to the right height, or the gantry is brought to the right height to allow the astronomer to come off the gantry and into the prime focus cage. That's what it would look like with the astronomer at the prime focus, with perhaps a photographic plate, checking that everything is lined up correctly. I don't know if astronomers actually wore 3-piece suits to do their observing. I doubt that, but a nice drawing nonetheless. And that's the area at the bottom of the prime focus cage. The prime focus observer would observe up here, but if they wanted Cassegrain or Coude focus, then mirrors in this lower compartment would fold into place to give you the desired optical configuration. And the coude room, remember the light comes down the polar axis of the telescope into the coude room, and then it would bounce off one or more mirrors and a diffraction grating, and then the spectrum would be recorded on a photographic plate. So it looks like everything is coming together. It looks like the telescope tube is basically done. The mirror has been ground to within a few millionths of an inch of the correct figure. So it looks like we're almost there. But we're not, because it's 1941 and the USA is about to be dragged into World War II. And that means the machine shops and the optical workshops get repurposed for the war effort. So basically all work on the telescope has to shut down for the duration of the war. So everything is brought out of mothballs in 1945 when the war is over. It's nice to see that the team responsible for grinding the mirror are now complemented by a number of women. That's excellent. And you can see that the mirror is now taking shape, because you can see that the surface is now close to a dish shape. You can't necessarily see that it's parabolic, but you can see that it's no longer flat. And it will take a little more grinding to get it to the right shape, and a little more testing. But there's a limit to how much testing you can do in the laboratory. You can do a knife edge test, yes, but ultimately the true test of a mirror is, does it focus a star correctly? And so basically they obtained the best figure they could in the laboratory, and then they said the final little bit of polishing will be done once we've tried it on a star. So the mirror was taken up the South Grade, that windy road, to the observatory. This particular image, the mirror is not in place. This is just a dummy at the bottom end of the mirror. But in 1948, the dedication ceremony took place. And at this point, the 200-inch telescope became the Hale telescope, celebrating George Ellery Hale, who unfortunately had died some years earlier. So Hale never actually got to see the Hale telescope in operation, which is a little bit of a shame. This image shows the dedication ceremony of the Hale telescope, and you can see the number of people who are on the observatory floor. I don't know, it was somewhere up to about 1,000 people were present at the dedication ceremony. Again, reminding you just what a huge telescope and observatory this actually is. This took place in 1948, so the Hale telescope came into existence in 1948, which was 75 years ago. So that's why I'm saying that the Hale telescope is 75 years old. It took a little more to tweak the mirror. The mirror was put into the telescope. There's no need to coat it with metal at this point. It's perfectly good to get a star image from the glass itself. You just pick a nice bright star that gives you a bright reflection without the need of putting metal on the top surface of the mirror. So the mirror was placed in the telescope, pointed at a star, and then they would see whether or not they're getting perfect star images. If not, they then identified which bit of the mirror seems to be a little bit high. Do we have a little mountain somewhere on the surface of the mirror that needs to be just polished flat, or at least polished away? So these little ticks are not scratches, they're just little marks that were made, telling the polisher, who I guess this guy is the head polisher, they are telling the head polisher that these points are just a few millionths of an inch too high compared to the rest of the figure of the mirror. So he would take these points, polish them down, then the mirror would be put back in the telescope, tested again on a star, identify any points which are just not quite right, take the mirror out, polish them again. It got to the point where we certainly are not using a machine at this level. The tiny changes necessary are probably just the polisher obtaining a little bit of jeweler's rouge on his thumb and gently wiping his thumb over the surface to take off a millionth or 2 millionths of an inch from different parts of the mirror. This would continue until the polisher was happy that the mirror was as close to perfect as they could make it. So in 1949 it was declared complete, and at that point it was then coated with a metal and it became operational. So here's a few publicity shots. Here's an astronomer sitting at the prime focus position just by the gantry that would allow ingress and egress to the prime focus position. And of course you can see down to the main mirror itself. This is a reminder from Russell Porter's drawings of what it is we're talking about. We're now looking in to the prime focus cage itself. There's Edwin Hubble in the prime focus cage. Edwin Hubble was very keen on using the Hale telescope to try and verify some of the ideas that he developed from data obtained on the 100-inch Hooker telescope. Of course, the prime focus cage is open to the elements and therefore during winter would have been very cold. And I'm sure that any astronomer that was in there taking data would have been very appreciative of any war surplus of electrically heated flying suits that were no longer available for the war effort and hence could be used in the late 40s, early 50s to keep the astronomers nice and toasty whilst they were sitting in the prime focus cage. This is an idea of what it would be like to work at the prime focus. Here we see an astronomer who's going to put a plate holder into position at the prime focus. So there's the plate holder going in and locked into position. Then he needs to get a photographic plate and put that in position. No, that's not the plate. Put it back. Okay, so in the dark he would open up the box to take out the photographic plate, place it into the plate holder. That's better, he's got the idea now. And then put the back of the plate holder in position to hold that nice and firmly. Okay, the photographic film is now in position. So to make sure that he's on target, he would then look through the eyepiece on the left to check that his guide star is where it should be. He might have to make some adjustments to the little telescope or eyepiece on the left-hand side there, just to make sure that the guide star that he's going to use is in the middle of a crosshair to allow him to ensure that the telescope stays pointing at his target. He would then check he's got his sandwiches. Yeah, okay, sandwiches are over there, so that's fine. Okay, we can now expose the photographic plate. Expose, and then do a double check that everything is okay. And over the next few minutes or few hours, depending on what it is he's photographing, he would check to make sure that the telescope was pointing precisely at the guide star. If there were any tiny variations in the motion of the telescope, he would have a paddle that would allow him to make tiny adjustments north, south, east or west to keep the guide star precisely located. If instead of the prime focus, the astronomer was working in the coude room, remember that light comes through the polar axis of the telescope into the coude room, as shown by Russell Porter's drawing on the right. Here we see a video of somebody actually working in the coude room. It's the other way round simply because the video camera is on the other side of the axis. So here the astronomer is looking up the polar axis of the telescope, checking that everything is set. He would then move that small telescope out of the way so that the light falls into the coude room. Another check that everything looks okay. If he's sending the light onto slits, that would then come through into the coude room itself. The light would hit one of these mirrors and then the diffraction grating and form a spectrum down here. So the astronomer is now placing a photographic strip of film at the focus where the spectrum will be recorded. Either the star or the nebula or the galaxy spectrum of interest. In the picture I showed you earlier, there's actually 3 people in the image. One of them is at the prime focus. We've just seen how that works. The other is in the coude room. We've seen how that works. The third person in this particular diagram is down here in the bottom right. It's the night assistant. This is the person who helps the astronomer and makes sure that the telescope is pointing in the right direction. The control desk for the night assistant is always in communication with the astronomer. They have agreed what the targets are for the evening, and the system has a set of dials that tells the night assistant where the telescope is pointing, and another set of dials telling the night assistant where the astronomer wants it to point. And a very clever set of self-synchronized motors then come into operation and basically change the orientation of the telescope until one set of readings matches the other set of readings. It's a very clever control system that was revolutionary for its time. And again, I can't really go into more details at the moment. Within a year or two, the Hale had taken this picture, which is of course where we started. 1951, a picture of the Horsehead Nebula, and I'm not sure how many other people it has inspired. I haven't got time to talk about what the Hale telescope has been doing for the 40, 50, 60, 75 years of its existence. Its contribution to astronomy has been many and varied topics and objects. But you might say, well, surely it can't be doing anything useful these days because it's 75 years old and has been overtaken by technology. Well, it's been overtaken by larger telescopes for sure. The biggest telescope in the world is now 10 meters in diameter, not 5 meters. It's only twice the diameter. After 75 years, it's only twice the diameter. But if you think of what it's actually been doing during those 75 years, yes, technology has moved on, but that doesn't stop the Hale telescope adapting in the literal sense. In other words, because the Cassegrain focus of the Hale telescope can take so much instrumentation, you can use it as a test bed for all sorts of new ideas. For instance, is it possible to take a standard telescope like the Hale working below the turbulent effects of the Earth's atmosphere and use adaptive optics, in other words, change the way the light travels through the various pieces of optics to compensate for the fact that the Earth's atmosphere is turbulent? So here we have adaptive optics that were used in 2013 to obtain an image of Ganymede. For comparison, we have a Hubble Space Telescope image of Ganymede, and we have the picture taken by the Hale telescope using adaptive optics. And it's not the way round you think. The Hale telescope image is on the left. The Hubble Space Telescope image is on the right. So clearly the Hubble has the benefit of not having any atmospheric turbulence to worry about, but the larger mirror of the Hale, if you use adaptive optics to compensate for variations of the Earth's atmosphere, you can get images which actually surpass the Hubble Space Telescope. That's why the Hale has been so useful. It wasn't simply useful for the length of time it was the largest telescope in the world. It's been useful even beyond that because you can still adapt new technology and use them in old telescopes. If you are going to continue using a telescope, you're going to have to maintain it. That doesn't just mean a new lick of paint every once in a while. It means you're going to have to clean the mirror. So every once in a while, they take the mirror out to be cleaned. If you're of a nervous disposition, look away now, because they have to get all of the grime of California off the mirror. They give it a wash, and then they spray it with a weak acid to actually remove the metal layer from the surface. Having done that, they give it another damn good wash and clean. Of course, they are much more gentle than it would appear in this video, the time lapse. They do not want to touch the figure of the mirror at all. They want to leave the actual shape of the mirror exactly as it was 75 years ago. But they want to remove any dust and grime, take it down to the glass, clean it, and then recoat it with another layer of aluminium, and then it should be almost as good as it was 75 years ago. And they do this every few years to keep it operational at optimum condition. So the telescope itself, as long as it's maintained, as long as it's given a new lick of paint, as long as they clean the mirror every once in a while, and as long as they have interesting ideas as to how they can put new technology in the rear end and actually use the light from the telescope and think about what they can do with the light, either at the Cassegrain focus or the Coude focus, there is no reason why the Hale telescope doesn't continue to produce cutting-edge astronomy and cutting-edge science for years, if not decades, to come. If you get the chance to visit, I can thoroughly recommend it. I found it inspirational to visit this and realise what you can do if you have the vision to build an instrument and the money to do it, how it can transform your view of the universe. So I've been telling you about George Hale, the billionaire whisperer who managed to get money out of rich people to build 4 of the world's largest telescopes. I've been telling you about how the site was selected, how the mirror was made, and how the telescope was made, and a little bit about what it's doing now. Let me finish with some acknowledgements and a final comment. I've obtained a lot of information from the Caltech archives and also the Corning Museum of Glass. Again, don't worry about making a note of these web addresses. I'll make them available to you afterwards. I'm also indebted to these various books. This one in particular, from David Woodbury, 1939. This is the one that started me thinking about writing a talk about the Hale telescope. It gives a lot of the background of George Hale's life before he actually built the 200-inch telescope. It was 1939 when the book was written, so the telescope wasn't actually operational at that point, but it gives a huge amount of information of the background. The books in the top right and bottom left are collations of the work of Russell Porter and his incredible drawings. I will send you a link to his drawings afterwards. The book in the bottom right, The Perfect Machine, is a more contemporary book. The Perfect Machine sounds a bit arrogant, but it's really the mindset of the people who built it. They did not want to compromise. They wanted the machine to be as close to perfection as they could possibly make it. So the Hale telescope was the largest telescope in the world before I was born. It was the largest telescope in the world during my childhood. It was the largest telescope in the world for half of my life. And it's been at the cutting edge of astronomy for over half a century. And there are very few scientific instruments that can make that claim. And it's testament to the scientists who designed it, the technicians who built it, the engineers who built it, and above all, the vision of the man who brought it all together, George Ellery Hale. Thank you for listening.